In this video, we're going to review the material covered in the course so far. We're going to review this through the lens of preparing for your midterm exam. And I want to start by having us review the course learning outcomes. These are listed in the syllabus that's posted on the Canvas website. So the first outcome reads that you should be able to analyze, derive operating conditions, and sketch transient voltage and current waveforms for common power electronic circuits. This includes DC-DC, DC to AC, and AC to DC converters. Let's unpack this a little bit. We're specifically talking about three things. The first is being able to analyze a converter. The second is to be able to derive operating principles. And the third is to be able to sketch transient and voltage and current waveforms. And we want to be able to do each of these three things for three different converter types. That is DC to DC converters, DC to AC converters or inverters, which we haven't yet talked about, and finally AC to DC converters or rectifiers, which is what we started the class on. So all three of these things are what we have been developing in class up to this point. The second learning outcome is that by the end of this class, you should be able to dimension and select key components in power electronic circuits in order to meet a design specification. We've been practicing this in class in our active learning exercises. We've had a few tutorials where I brought up data sheets and we've looked at DigiKey. And in your homeworks, we've actually had you go out and select components by searching for values within DigiKey. The third learning outcome is that by the end of the class, you should be able to analyze the performance and conduct basic design steps for closed-loop regulation of power electronic circuits. So this learning outcome we have not covered yet. That is going to be, we're going to be starting that unit after the midterm exam. So to be clear, what is eligible for the exam is learning outcome 1, and pertaining specifically to DC-DC and AC-DC converters. And then learning outcome 2, we're talking about dimensioning and selecting key components in power electronic circuits. So let's now talk about this as it pertains to the individual units that we've had in class. So we've covered several distinct pieces of material pertaining to power electronic converters, and we started the class by talking about AC to DC converters, and specifically a full wave rectifier, the single phase low frequency rectifier. And in all cases, we were considering this circuit where we had an input voltage, and we acknowledged that this input voltage was coming from a transformer. The input voltage had a series resistance and was connected to a diode bridge. On the output side, we placed a capacitor and a load of some type. At this point, I'm going to label it as a load resistance, but we acknowledge it could be modeled as a voltage source or it could be modeled as a current source depending on our needs. And we labeled a few currents on here. So with this circuit, we practiced drawing the waveforms for each device, for the diodes, for the capacitor, for the load resistance, for the input of the circuit. And we drew these waveforms in terms of both currents and voltages. So you should be prepared and ready to analyze this circuit and recreate those waveforms. Specifically, we also talked about equivalent circuits. We talked about how we can study this circuit as the following equivalent circuit when the diode is conducting. So during the on state, the circuit reduces down to being a voltage source, a series resistance connected to a voltage source load, where a voltage source load we described as being VDCE, or VDC equivalent, and said that it was equal to 2 times the diode voltage drop plus our output voltage, Vout. And this was only valid when diodes are conducting. We talked about a way to analyze when the diodes will turn on and off by drawing the turn-on voltage, by drawing our input voltage superimposed upon a line showing this equivalent DCE voltage, and noting that when the input voltage crosses this line, the diodes turn on or off. So when the diodes turn on, this was called our inception time, and when the diodes turn off, this is our extinction time. And our current simply looked like the voltage applied across a resistance Rs. So you should be able to recreate these figures. You should be able to analyze and internalize these figures so that we can ask you fundamental questions. We're not looking for you to memorize equations. This exam is not about equations, it's about understanding the operation of these converters, how to analyze them, how to drive their operating principles, and how to sketch their transient and voltage and current waveforms. So again, everything goes back to these learning outcomes. And you should also be able to do this for an arbitrary shape waveform. For example, I could tell you that the input voltage waveform has some kind of bizarre triangle shape with different maximum and minimum peaks, and you should be able to tell me when the diodes are going to turn on and off what the various voltage and current waveforms look like. We did a learning exercise like this in class. Okay, now let's talk about the next item that we covered, which was power electronics steady state and waveform analysis. So specifically I'm referring to our discussion regarding RMS quantities, average quantities, regulation, efficiency, and power conversion. If there's one equation that I do want you to memorize, it's the RMS equation. And you don't have to memorize this as an equation. We talked about how to remember it based on its name, where RMS is an acronym for root mean square. So this means that we take the square root of the mean of the square of our signal. And mean is just a fancy word for average. So from this description, you should be able to write out that this is the square root of the mean of the square of our signal. And if we're talking about a current, this would be I squared dt. So we square our signal, we take the average of it, and then we take the square root of it. An average of a signal is simply the signal integrated over one period and divided by the length of that period. We defined line and load regulation, where line or load or fill-in-the-blank regulation refers to the amount of error that is caused by changes in the fill-in-the-blank quantity. So if we're talking about line regulation, we're talking about the amount of error that occurs in our voltage output due to changes in our line input. So line regulation we defined as being our desired output voltage minus our actual output voltage and divided by the change in our input voltage from its nominal condition. So a low regulation number corresponded to the circuit having low error for a high swing of the input voltage. A high regulation number, say 50%, meant that we had a high swing in our output voltage when our input voltage had a high swing. So we want to have a regulation that has a very low value. You would like 0% regulation if it was possible. Also, we should be able to talk about, you should be familiar with power conversion and power conservation and efficiency. So you should really internalize these concepts because they come up time and again in this class. That if we have some arbitrary circuit and we connect to it a source, which means that we have an input power going into it and that has some kind of voltage and some kind of current going in, we can talk about the power that comes out of it, and it will have a voltage and a current again. And we can say that the output power has to be equal to efficiency times our input power, or equivalently we can write that output power is equal to input power plus our losses. Next, we've spent a lot of time talking about the single pole double throw converter primitive, and specific topics that you should be aware of include conservation of energy, the steady state equivalent circuits, transient waveforms, its design as a buck boost or a buck boost converter. And this primitive circuit, which we've sketched time and again in class and in our active learning exercises, is of the following form. We have 2 throws and 1 pole, and across the throws we've defined a throw voltage, and across the pole we've defined a pole voltage. So we have a top throw, throw 1, and a bottom throw, throw 2, and then we have an output current, which is our pole current. So you should become very, very familiar with this converter for this exam. And you should be ready to talk about the relationship between the pole voltage and the throw voltage, and the various and the two throw currents as related to the pole current. So we've talked about this in terms of conservation of energy, that the power that flows into on the input side from your throw must equal the power that comes out your output side out of your pole. We've talked about this in terms of Kirchhoff's current law and Kirchhoff's voltage law. We've talked about this in steady state conditions where we are operating in a constant duty ratio. And we've also talked about this in terms of transient conditions where we're considering exactly which throw our pole is connected to. And I really want you to internalize the idea that this is essentially a voltage divider in an average sense. What I mean by that is that in a conventional voltage divider, we have resistors that are used to divide the voltage between the two resistors to some output voltage. But in this converter, we don't have resistors. Instead, we just connect our pole back and forth between the two throws so that we get an output voltage on our pole that is less than our throw voltage in an average sense. So in the instantaneous sense, it's either equal to our throw voltage or equal to 0. But in the average sense, our pole voltage becomes the duty ratio of the top throw times our throw voltage. So you should be comfortable with expressing the pole voltage in terms of the throw voltage, and you should be comfortable with expressing the throw currents in terms of the pole current. We've talked about how you can go from this converter, from this single pole double throw converter primitive, and how you can model it as a steady state equivalent circuit consisting of dependent current sources and dependent voltage sources. And we've used this steady state equivalent circuit to construct a DC equivalent circuit, which we're able to use when we have resistances in series with our source voltage, or we have resistances in series with our pole current, for example, our inductor. So you should be comfortable with this equivalent circuit in the continuous conduction mode and discontinuous conduction mode. We'll talk more about those, the CCM and the DCM modes, in a little bit. We've also talked about how you can implement this circuit as actual semiconductors. So you should be comfortable with how you go from the single pole double throw converter primitive to the semiconductor realization. We define this in terms of the direction of the pole current and the polarity of the throw voltage. So when we know the direction of our pole current and the polarity of our pole voltage, we can then sketch the semiconductor realization. So I'm going to sketch this now for a positive pole current and a positive throw voltage. And this was the active-passive realization. We've also discussed an active-active realization where both of the devices are active devices. By passive, I mean that we've used a diode. So we've talked about a way to check if this realization is correct by considering what will happen to the current path when the MOSFET is off. So we've commented that there always has to be a current path for the pole current in this converter, and you can see in this case our pole current is defined going left to right, so it's a positive pole current. When we turn our MOSFET off, we can see that we do indeed have a path for the pole current through the diode. The diode can turn on. However, if we had drawn the diode the other way, this would not work. You would cause some device to blow up. The circuit would fail. Furthermore, we have a second sanity check on the implementation of our semiconductors, in that we can check what happens when our MOSFET turns on. If the diode is connected as shown, the diode is able to block the pole voltage, or the throw voltage. But if the diode were connected like this, we would have a short circuit as soon as our MOSFET turns on. So you should be able to use these checks to determine whether or not a semiconductor realization is valid. If I show you a semiconductor realization of a converter, you should be able to tell me if it is valid, and if it is not, how to correct it. Next, we've talked about current and voltage stiffeners. These are capacitors and inductors. how to dimension them. That means how to calculate the required value of capacitance and inductance. We've sketched transient waveforms when considering these devices in real life, considering the ESR and ESL. And at this point, you really should know the differential equations for these devices. That is, it should be fresh on your fingertips that the voltage across an inductor is equal to L di dt, and the current through a capacitor is equal to C dVc dt. And so you should be very familiar with how to use these differential equations in order to calculate the required inductance or capacitance to satisfy a ripple current or a ripple voltage requirement. And this is true for both the single pole double throw converter as well as for the single phase full bridge rectifier. So we should be able to go from these equations to select values of L and C based on delta V and delta I. We've also talked about the equivalent circuit of these devices, how when you think you're buying a simple capacitor, you're actually getting an equivalent circuit that has a resistance and an inductance and a capacitor. And we've quantified these, we've labeled these as an ESR, and ESL, and our desired capacitor. We've talked about how to read data sheets to determine these values, and we've talked about how to read data sheets to see how components derate based on temperature and based on frequency. I should be able to give you a capacitor current waveform of an arbitrary capacitor current, for example, like this, and you should be able to sketch for me what the voltage looks like across the capacitor. So this is true both for when you have the simplistic capacitor that just consists of a capacitance, and for when you have a real-life capacitor that has both ESR and ESL. And the same thing is true for if I give you the voltage waveform for an inductor. You should be able to sketch the inductor current. So we've also talked about the semiconductor switch realization of single pole double throw converters. I talked about this a couple bullet points ago when I mentioned the single pole double throw converter primitive, but now I want to highlight our calculations of power losses and the turn-on, turn-off waveforms of these devices. So when we're talking about semiconductors, we're specifically talking about diodes and the transistor, whether it's a BJT or it's a MOSFET. And for diodes, we talked about the conduction losses. We've also talked about reverse recovery phenomena tied to diodes. We're not going to be considering reverse recovery for our exam, so don't worry about being quizzed on reverse recovery characteristics. For the active switches, the MOSFETs, the transistors, the BJTs, and the IGBTs, we've talked about both conduction loss and switching loss. And switching loss we calculated by looking at the switching waveforms. So we define this for a single pole double throw realization with a positive pole current during both the turn-on event and the turn-off event. During the turn-on event, we saw that for our MOSFET, our drain current rose over a finite interval, which we labeled as a rise time, and our drain source voltage then fell over a separate interval, which we labeled as our voltage fall time. So this was turn-on. This was the turn-on characteristic, but we also have a turn-off characteristic where the reverse happens. First our voltage has to rise, termed a voltage rise time, TRV, and second, our drain current had to fall. And we showed on these plots how you can match this up to what the gate source voltage is doing, because the gate source voltage is what drives this entire phenomenon. So in the turn-on time, initially we had a delay time, which we labeled as TD on, during which our gate source voltage was charging up from 0 to the threshold value, and At the threshold value, our gate source voltage continued to increase, but now our drain current was able to increase, and so this happened up to this point. And now at this point, our gate source voltage became pinned at the nominal current until our drain source voltage was able to collapse. And then our gate source voltage rose the rest of the way to the value that our MOSFET gate driver applied. Our MOSFET gate driver was applying a gate source voltage of VGG. And a similar thing happened during the turn-off event. So you should be familiar with these waveforms. You should be able to analyze them and construct them. You should be able to sketch them, both the turn-on and turn-off. For conduction losses, we considered calculating conduction losses for the MOSFET based on the channel resistance. So our drain current, our RMS drain current, times RDS on. And we considered calculating them for the diode in terms of our forward voltage drop and our average diode current. So I want to clear up some confusion that has come about in the class with the conduction loss expression. So a couple students have asked me why it looks like the conduction losses are calculated differently for the MOSFET as for the diode. And in actuality, they are not calculated differently, and we can prove this right now. So for our MOSFET, we talk about the MOSFET channel as having equivalent resistance. And for the diode, we talk about the voltage drop across the diode as just having a defined value of VD. So let's consider this. Let's draw a graph of what I'm going to draw is the current waveform. And it doesn't matter whether this is a MOSFET or a diode. Let's just say that we have a square wave current waveform. And it has some on time of D times TS. And then it's off the rest of the time. And then let's say that we have a voltage graph, a voltage waveform that is non-zero only when the device is on. And it doesn't really matter what this voltage waveform is doing when the device is off because there's no current flowing. There can't be any losses when there's no current through it. So our voltage graph has some height. Let's just label this as VD, and we'll label our current peak as ID. So we have let's say it's I hat D and V hat D. And let's now calculate our average power that is consumed by this device. So this could at this point be either a MOSFET or a diode. There's a current going through the device, and then there's a voltage drop that's appearing across the device. And if we look at power, we would say that it's 1 over T, the average power, times the integral of I of T times V of T over the switching interval. And so if we evaluate this integral, we can see that this is going to give us 1 over T times dTs I hat D V hat D, which is in fact equal to D I hat D times V hat D, which this quantity right here is just our average current. So this is equal to ID times our voltage drop. So this looks like our diode's conduction equation. Now, let's say that let's visualize the voltage drop in terms of a resistance. So let's say that V hat D is equal to I hat times RDS on. So this would be the voltage drop of a MOSFET that has an equivalent resistance of RDS on. So let's plug this into our expression right here, and we're going to get that our conduction loss is equal to D I hat D squared times RDS on, which is clearly not the same thing. D times I hat D squared is not the same thing as the average current. But out of curiosity then, let's calculate what ID RMS is. And that is defined as, and if we evaluate this integral, which is simply equal to D square root of D times ID hat, that our power loss is in fact the square of our RMS current times RDS on. So this proves that PC is equal to ID RMS squared times RDS on. So the point of this is that our fundamentals are consistent. And we're calculating the same average power regardless of whether we visualize the voltage drop across our device as being a fixed voltage drop that we took from a data sheet based on the current through the device, or whether it's based on the resistance. But we have to be intelligent about how we calculate the losses. So you can always go back to your fundamentals and sketch the waveform and derive the average power flowing through that. Or you can realize that RMS current squared times resistance is always going to be equal to real power loss. Finally, let's talk about the thermal analysis and heat sink selection unit that we covered. We talked about how semiconductor devices consist of some die that's encapsulated within a broader case, and oftentimes that case is then fitted to a heat sink, and all of this is responsible for conducting losses from this device out into the broader world. To analyze this, we considered a thermal circuit where we had our power losses in our semiconductor modeled as a current source that is fed into thermal resistance elements. And this thermal circuit includes a voltage source, which is actually our ambient temperature. So we talked about how we're converting power loss into current sources, how we're converting thermal impedances into resistances, and temperature differences into voltage sources. So for this model that I sketched here, the first resistance would be R theta junction to case. The second resistance would be R theta case to sink, and the third resistance would be R theta sink to ambient. And if we were to measure the voltage at any of these points, we could determine the temperature at that point. So the voltage from this point right here, or relative to this, is going to be the temperature of our MOSFET junction. The voltage at this point right here is going to be the temperature of our case, and the voltage right here is going to be the temperature of our heat sink. So these resistance terms were given in units of degrees Celsius per watt of power that has to flow through the thermal impedance. Finally, you should be able to define continuous conduction mode, discontinuous conduction mode, and sketch voltage and current waveforms that correspond to either conduction mode for a DC-DC converter. You should also be able to calculate the critical conditions of the converter. So we defined critical conduction mode and discontinuous conduction mode in terms of the inductor current waveform. We said that if we're graphing the inductor current and the waveform never is zero for any prolonged period of time, then we are in continuous conduction mode. However, if we draw this graph and the inductor current goes to zero for a long interval of time, then that is discontinuous induction mode. The critical conditions correspond to the conditions that make the inductor current touch zero but not linger at that for any duration. So another way to say this is that we are in critical conduction conditions if our average output current is equal to delta I L by 2. Here's what that looks like. that means that our inductor current rises and falls and just barely and just touches 0 amps for an instant of time but does not stay there. So in other words, if this is our average inductor current and this is our ripple current, that average inductor current is equal to delta IL by 2 when we are in the critical conduction condition. And we talked about critical components as being components that are sized to place us in that situation. So if we talk about the critical load resistance, our critical, this is the load resistance that if we were to increase it any further, we would enter discontinuous conduction mode. So increasing the load resistance means that we're decreasing our load. We're drawing less power for the same output voltage. L critical is the critical inductance, at which if we were to decrease that critical inductance any further, our ripple current would increase so much as to put us in discontinuous conduction mode. And I out critical is our critical load current, that if it were to decrease any further, we would be in discontinuous conduction mode. Or in other words, our average inductor current would decrease too much so as to put us in discontinuous conduction mode. So these are the main topics that we've discussed so far in this course. And just to bring you back to the fundamentals, what I'm trying to assess in this exam is how far you've come in being able to analyze, derive the operating principles, and sketch the transient voltage and current waveforms for common power electronic circuits, and specifically the DC-DC converters and the AC-DC converters. And secondly, I'm trying to assess your ability to dimension and select key components in power electronic circuits in order to meet a design specification.